All right, let's try an example. Example 2.3.4. I'm going to consider the linear transformation S from R2 to R3 that sends xy to 3x minus y, y, x plus y. And I'm going to take t from R3 to R3 that sends xyz to 2x minus y, z plus y, and to x plus z. So I want to use this example to study the equivalence between matrices and linear transformations. All right, so I have two linear transformation. In A, I'm asked to find matrices S and T. So we have a shortcut for this. All we have to do is apply S to the two standard bases vector. And so if you apply it to 1, 0, you get 3, 0, 1. If you apply it to 0, 1, you get minus 1, 1, 1. Or you could do it like we did in the first example of this section, where we just kind of spelled it out and checked which coefficient we needed. Really, these are the coefficients of x, these are the coefficient of y. All right, we do the same thing for t, but of course now t is from R3, so we have 3 basis vectors to check. So if I apply it to 1, 0, 0, that's x equals 1, the other ones are 0, so I get 2, I get 0, and I get 2. The next one is y equals 1. I'll get minus 1, 1, 0. And the final one is z equals 1, so 0, 1, 1. All right, so there are my two matrices. All right, use T to find the kernel and the nullity of T. So the kernel of T we just learned in the last proposition right here. Oh, that's the proof. That the kernel of T is a null space of the matrix. We have the matrix in A, so we just need to find the null space. So kernel of T equals to the null space of 2, 0, 2, minus 1, 1, 0, 0, 1, 1. So I'm going to reduce this matrix. I've already done it, so let's just skip ahead. This is what I have. So I'm thinking of this as the coefficient matrix of a linear system. You can think of it as 0, 0, 0 hanging out here. I have a free variable here. And so x is minus 1/2 of s, y is minus s, and z is s. All right, so the null space would be the span of the vector. I have only one parameter, so only one vector, so minus 1/2, minus 1, 1. And so the nullity, which is the dimension, is just 1. All right, then I'm told to use T to find the image and the rank of T. Notice that from the nullity, I could get the rank. It's just dimension of V minus, so dimension of V is 3 minus 1, I should get 2. But let's see if we could, figure it out. All right, so what the proposition told us is that this is the column space of the corresponding matrix. And so to find that would be the span of the columns of T, so of 2, 0, 2, minus 1, 1, 0, 0, 1, 1. I need to find a basis for this. So when you reduce, remember you keep the do you remember which vector you kept? So you look at the leading entries and you keep the corresponding columns. And so in this case, since we have two leading ones, we only keep the first two column. So a basis for image t would be 202 minus 1, 1, 0. And so the rank of t is the dimension of image t. I have two elements in the basis, so it's 2. But of course, the rank nullity theorem already told us that it was going to be 2, but it matches what we found. All right, so let's keep going. Now I want to find the matrix corresponding to the composition in two ways. I want to do it directly. That means I'm going to write out, spell out what the composition does to one element, and then from that get the matrix. And then I'm going to do it by using the matrices from S and T that I already have. So, all right, I want to know what T and S does. S from in R2, so it was XY. So that means T of S of XY. I don't remember what it was, but I have it in my notes, so let me just write it out. That was 3x minus y, y, x plus y. Is that right? 3x minus y, y, x plus y. And then I'm going to apply t to it, so I'm going to take twice the first minus the second. So twice the first entry minus the second. And then third plus second. And the final one was twice the first plus third. So twice the first plus the third. All right, so I got 6x minus 2y, well, minus 3y. Let me do it directly. The next is x plus 2y, and the final one is 7x minus y. All right, so we can find the matrix of T composed with S either by trying to write this as a product of a matrix times xy or by applying this linear transformation to 1, 0 and to 0, 1. That's going to give me my two columns. All right, so 1, 0 would give me 6, 1, 7, 0, 1, minus 3, 2, minus 1. All right, now I want to use the matrices that I found in A to find the matrix of T, a matrix of T composed with S. So we're told to take the matrix of T and the matrix of S and multiply them. All right, matrix of T, this one 202, 1, minus 1, 1, 0, 0, 1, 1. And S, I have it here, 3, 0, 1, minus 1, 1, 1. All right, so I just multiply them like I would multiply matrices, so this times this, and so on. So I'll get 6, I'll get minus 2, minus 1, so minus 3. I would get 3, 0, 1, 0, 1, 2, 6 plus 1, 7, and minus 2 plus 1, minus 1. All right, and we proved it, so hopefully you believed me, but now we have an example to show you that it works. These should be equal, and they are equal. right? So often for these questions, you have a choice. Either you play on the level of linear transformation or you go to matrices and the answer will be the same in the end. I think at this point, we're probably more comfortable with matrices and it turns out to be very algebraically straightforward and you always do the same thing. And we've done tons of these examples. So it's quite nice to go back to matrices and feel comfortable. I think it was a bit abstract before. This is more hands-on now because of matrices. All right, so that's it for today.